I just discovered something recently that was interesting. You know when it says, uh, "Do you accept these cookies?"
Yeah, and I deny them all the time.
I started rejecting them and nothing happens.
No, you can still do the web page.
Everything works.
Yes.
So
yes.
just fucking reject all.
Yeah, yeah. I do that.
I figured like the web would break.
Uh-huh. What?
Oh no, I'd rather be swearing over the speaker.
Okay. Let's see here. Is there a? I'm gonna just. Is there a clicker too?
Yes.
Where?
I had it there
Is there?
behind.
You know, you pointed out it's translating.
Oh, okay. That's all right. Let's see. I'm gonna just, I haven't said anything. It's not. Oh yeah, it works. It works. It works. Okay.
It didn't catch it.
Okay.
All right.
Get bored with my own discussion. All right. Bienvenido al grupo de trabajo LSR. Ahora basta de español. Okay, so we're going to get started here. I'd like to. I'm going to give the status slides, even though Ying Jen was nice enough to make them. And we'll get started. Okay, here's the note. Well, it just says that if you know about IPR and you're participating in the IETF, even if you're not on the draft, you're obligated to disclose it just by your participation. Also, there's a whole bunch of BCPs on behavior and respect for your colleagues. So we debate the technical issues without calling into question anybody's character or intelligence. Here's additional administrivia. Okay, here's the status. We have one RFC since IETF 122, the prefix extension flags. This is good to get because it's kind of a base document. We probably ought to do the AnyCast where we had for OSPF V2 or V3, I think it's V3, we have a gap where it's not specified, but now we have the flags that were dependent on this RFC. We have the admin flags, so for OSPF, not the admin flag, admin tags for OSPF. I'm an offer on this. We really needed this because we only had tags for the external routes and NSA routes. Now we have them for all. We got IGP flexible algorithms. This was a good piece of work. This is also on the RSC editor queue. We have multi-part TLVs. That's a good piece of foundational work that allows us to extend ISIS to bigger, more TLVs. Beyond the single byte length. And we have these two Yang models. These were waiting for a while. They had normative references because we were configuring TILFA, which was in the routing working group. But now TILFA is also on the RFC queue, so we'll be able to publish them all. And this one's in there's in the IESG telechat. Peter's been working on the discusses, and I'm hoping Roman's he'll be satisfied with the response and the fact that we're using a registry now to maintain the strict ordering of application of link constraints in the flex algorithm. We adopted this draft, and it's on the on the agenda today. Tony's going to present, Tony P. And we completed the working group last call on the experimental IGP unreached draft. We're wondering if this draft is ready for last call. We were going to last call it before we decided to do about a year and a half ago, but we decided to do the link bandwidth first because there were a couple implementations of that draft. So we'll, in this working group, we'll always put drafts that have been implemented ahead of drafts that have not. So, but this is expired, so we're hoping. Anyway, it's a gap for the adjacency related SID per algorithm. And let's see if I'm going to say anything about these. I'm going to say something about the first two. The first two, these are the flex. We split out the flex algorithm extensions. What we were doing for drafts that didn't have Yang augmentations, we were putting them in one bundle. Well, we decided to split out the flex algorithm ones and do them right away because we've been sending a lot of flex algorithm documents to the IESG, and they're always saying, well, where's the Yang? So we got to give these a priority and last call these. I guess I reviewed Ying Zhen and a new offer, Madhavi Joshi, did some work on splitting these apart, and it'll be good to get those done. So we'll have a base that we can say, okay, here's the base flex algorithm we're going to do. Every time we do a new flex algorithm draft, we can say we're going to augment these as a base. And you see the last two, there doesn't seem to be either a lot of interest in these drafts, and there definitely isn't any interest in implementation. So I don't know, we'll probably quit carrying these on the status because we've got drafts that we really want to do. Let's see. Yeah, those two drafts at the top, those two OSPF drafts, we probably could last call both of those. But they're not as high a priority as getting those Yang models last called, so we'll have something to point to that we're doing Yang models for our extensions. And we recently adopted this draft. Probably should have been on the slide. This is a consequence, another one that had the newly adopted one. This is an experimental draft from Tony Lee and Sarah Chen from work that was done at Arista. And we're going to do this as experimental because there's at most one implementation. And a lot of the flooding drafts we've done because unless they're implemented by, they're fairly complicated, and unless they're implemented by multiple vendors, we're doing them as an experimental. And finally, we're thinking we've had requests to adopt all of these. So I'm not sure which one we give priority to, but the top one is the oldest one. Maybe we should, the first time we talked about that, there was the biggest sticking point on it was how do we measure link loss, which is kind of ancillary because we have the extended metrics where we have these metrics anyway, and given that we have those, we should be able to apply them to flex algorithm. The reverse prefix metric, one reason we might want to do this is because in SABnet, if we end up with reverse SPF as the primary tool for detecting asymmetric traffic and allowing the RPF to work for asymmetric traffic, we might want to do this, even though there is, as Peter Senek pointed out, even though there is a way to do it with flex algorithm, that's kind of a high bar, given that really flex algorithm is really, of our three IGPs, OSPF v2, OSPF v3, and ISIs, it's really only implemented by a lot of people in ISIs. And there was a request for soft David plane. So that's it. Without further ado, we'll bring up the first. Okay.
Sometimes we've run, I don't know if we're going to do that with this, but sometimes we've run multiple last calls with like Yang plus other technology drafts. So I'm just curious if anybody had any objections to running the flex algorithm Yang and then maybe starting some last calls on some technology. Okay, thanks.
Is there any volunteer for meeting minutes?
We'll just copy the transcription into the meeting minutes. Tony P, yeah.
I see you keep the presenters very close now, so you can hit them when
That's
they say
right,
something
yeah,
nice.
yeah.
Okay.
Or like a gong show.
Here, Tony, here's this. It works. Just point it at the.
Thank you. Okay, Tony P, HP, former affiliation is well known. So I try to not go, too long today, but good amount of material. First, let's talk about what happened, a significant update to this distributed flood reduction stuff. There was a lot of discussion on the list, progressing the kind of stuff. That also kind of encompasses like the architecture stuff because it was all hanging together. Goody. So, no, wait, which one is that? No, that's too early. That's,
You got it in the wrong order.
yeah, it's the wrong order.
It should be
Can you flip me on like the first, like the update on the draft?
flood reduction.
Please. Yeah. All right. So that stopped working. Technology. All right. Right. So what happened? At least from our side, there was lots of implementation, test, measurement data on real topologies, which of course I cannot show, and something where we did I show you synthetic results, which in terms of properties of what we were measuring, the graphs, the relevant properties of the graphs are the same as what we see with the real topologies. So I think you can from here draw a lot of conclusions. Then there was a lot of discussion in context of all these, flood reduction architecture thingy, right? How to reconcile all this work. When we were implementing and testing, we found, a couple of interesting things like, how do you deal with broadcast? We have to close all these things on the draft in terms of, features and behaviors. So there was a bunch of modifications to talk about. And the interesting thing is we played a lot with the hash function. So a lot of stuff fell out there. So what was the technical changes on the distribution draft, distributed flood reduction? The broadcast medium will basically spend good amount of talking, how should we deal with broadcast mediums, right? And with the DIS and so on. And the simplest was that we basically modify computation and we put it in the draft that you basically jump over the DIS and everybody across the broadcast medium is basically one hop away from you. That doesn't change any of the DIS behavior. And in case of the reduction misses the DIS, right, then that this is still generating CSNP to heal the flooding in case there's any kind of problems. The other thing that was interesting, we had some over clever implementation, and we realized that we better add to the draft that in case when you're processing CSNPs and PSNPs that you're receiving, you better not try to optimize flooding, because that will defeat any kind of, of healing mechanism. So we specified it clearly in the draft that, that has to omit any kind of optimization. And that also means that, even if you are not a flood leader and you're receiving CSNP from the other side, that may interfere with the reduction stuff, because you really shouldn't flood, but you end up flooding because the CSNP that hits you forces you to flood, which for practical purposes, didn't make any measurable difference in behavior. The hash that was in the draft was actually very poor when we started to measure that, because it wasn't distribute the load very well, okay? So the first thing was that the fragment ID was the first thing that was shifted all the way to the left. And I say why that matters. And the last byte of the system ID, because it was shifted in last, or it was put in last at the very right of the hash that we were using then to build the modulo, was basically determining in cases of 2 or 4 available flooders, the 4 bits were basically determining who would be the leader, right? Because those bits on even on modulo on even numbers were pretty much triggering, everything. So all the other bytes didn't have any contribution to entropy. And the worst of all, and nobody actually caught up on that, is that when we were building the hash and the last byte was shifted 4 bits to the left, we didn't shift it back. So the 4 bottom bits were always 0. So in case of 2 and 4 and so on and 8, we were basically ending up always on the same guy because the value was always 0. Now, yeah, embarrassing, yeah, but nobody caught it on. So the hash, after experimenting with the stuff, that actually balances quite well, is that first we add the byte position. So we don't only shift in the value, but we basically add +1 to the first byte of the system ID, +2 to the second, and so on. And that defeats actually very regular numberings, right? When people assign the system IDs very well. And the last system ID byte is not rotated, and we actually made the hash shorter. Instead of 64, we made it 32, and we're basically folding up the 32 onto each other. So the high order bytes now start to influence the modulo, the lower bits. I know very technically you can read it. We used to have the pseudonode ID. We kicked it out, so it's not into the hash value. So it's basically treated like the originator. Didn't make any difference, simplified everything. The reference implementation in Rust actually totally mismatches the text, because I pushed it to the upload before I updated the text. And there was one more thing. Oh yeah. So the interesting thing where we're thinking about all the hashing stuff, but it will come up with another presentation of this hierarchical SNPs, is that an easy way to achieve a better hash distribution, more even distribution, when I talked to some guys who dealt with it, is basically to double hash using 2 different hash functions and then sort them on top of each other. So we may actually go there. For the moment, it looks like the balance is pretty well. I mean, you will see like empirical results how this hash behaves, right? Good, what else? So now a big change is that the draft was also dealing with some signaling. That is all out. It's basically pure algorithm. So it can be used anywhere and needs a value from the existing IGP algorithm type for computing flooding topology. Mouthful now. So, we need to assign value for the stuff before we start to squat on something. And the flood reduction architecture draft has been simplified. Actually, I don't have much presentation about the stuff. And it can be used to signal that stuff. And the signaling is really in the ISI's flood reduction architecture draft and in the existing RFC, right? Good. And what do I have? Yeah, so I just have one view graph on the reduction architecture just to refresh with people what it was, because nothing much changed on the draft, like I say, except, yeah, some no minimal amount of stuff changed. So basically, the way the thing works is that each node signals via router capability TLV, at most one running algorithm, right, that it uses to do a flood reduction. When nothing gets signaled, it means that it's standard flooding, which can be used, in the logic if somebody wants, as we do not recommend it, but it's a valid behavior. The draft allows it, and everybody who finds on the other side of the link the same algorithm, they build something called a connected component. And within that, people can run any kind of centralized distributed algorithm that basically removes links from flooding, like here, these red crosses. Obviously, assuming that they built something which is connected, so the flooding reaches everywhere. And the draft mandates that you find a different algorithm on the other side of a link, you must flood, which leads at the end to a fully connected graph. I mean, not optimized anymore, because you flood across every link that connects to components, but it guarantees that no matter how many algorithms you run and how they're distributed, that the whole thing at the end has a connected flooding topology, to use the term AC likes. Good. Yeah, so there's a minor note is, of course, here that when we started to look at the broadcast stuff, that basically, unless everybody on the broadcast agrees on the algorithm, it will lead to basically full flooding, which is okay. Right, so that's, I think, that has been added to the draft, that on the broadcast, you have to see whether everybody runs the same algorithm, otherwise flood. Given that the broadcast things are practically speaking, vanishing very quickly in terms of list ISIS, this is something we have to specify, but I don't think it practically has much of a significance. And I think that's it. Yeah, so, AC?
I guess I'm at the head of the queue. AC Lindum, Arcus. I think it's correct that this architecture, this flooding reduction architecture, should be standard track, but I think the one with the flooding reduction should be, and the hash and the incremental, what do you call them, SNPs, the incremental SNPs, that should be experimental. It's right now it's standards track.
I have no idea. I copy paste
anyway,
happily files and then I change titles.
Okay, yeah. I mean, but
Okay.
I agree that this one, the one that defines the interoperability, should be standard track. But I think the other one should be. We generally, for complicated, like I said, for complicated flooding reduction algorithms, we've made them experimental unless we have multiple people that are going to implement the same one.
Yeah, no, ultimately it boils down to how many vendors and interoperability and how many customers will deploy that, right? The rest is boilerplate. At least for me, that's how I view the world, but I'm a simple man. All right, I think that's about it, unless there are any questions. Good, so we can jump to the empirical results, the one with the blackthorn thing. And all the beautification has been generated by AI, which I randomly clicked right in the PowerPoint, just to not make it terminally boring.
So just for everybody's edification, the first presentation covered both of the two drafts, and this one is results of actual experimentation they did at Juniper, this presentation.
Yeah, I mean, I didn't want to do a lot of repetition and bore everybody to death. I mean, I assume everybody who was mildly interested in the topic followed the very vivid exchanges on the mailing lists, right? Good, so So what was the point, right? We have this algorithm implemented first. There's a lot of simulations, and I wrote stuff in Python that is actually doing the calculation of real custom topologies, whether the thing will actually bias anything, blah, 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 right? But this is actually real implementation. And what I can show you here is a good approximation of large customer networks in terms of graph theoretical properties. And what was the most interesting stuff was actually this, in practical terms, is to have a stable topology with large number of LSPs, adjacencies, blah, 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 right, that will experience heavy LSP injection. I mean, that's what we're seeing as, during heavy load scenarios where we really take things all the way out the envelope, right? So the reasons may be different. People redistribute, people reconfigure the wrong way. We have some massive resource allocation storms. The reasons are always interesting. One thing that we wanted to look at is whether giving things significantly more CPU will change behavior. We wanted to see what happens when you have few sources that misbehave or just for legitimate reasons really reissue a lot of stuff. When you have a lot of sources, we were looking also at flooding speed. Does it have any implications? Because that is, of course, what is going on at the same time, right? We're considering how important will be giving people faster flooding speed versus this thing in combination. Like I said, it's a real implementation. That's basically production code implementation. And yeah, we looked, does it converge, right? That's like the first question, right? When this thing is in the network, do we see convergence problems? Because then, that's a different order of problem to deal with. How fast does it converge? That's always, big question. Then what's the volume? What's the load, right? CPU, how much LSP, SNP? Because during such significant, I wouldn't say outages, but spikes, it is not only the IGP or ISIS that runs, mostly that triggers enormous amount of things on the box, and we're really competing, right? That's why does a lot of CPU help it, right? And what is the CPU consumption? That's a very significant metric. Faster flooding, like I said, and when do we hit retransmission envelope? Because this is an inflection point. The moment you start to hit the retransmissions, and basically things go down the hill very, very fast from practical experience. So that's why. Now, how did we test it? Yeah, here I got a little bit excited. It took most of the things, so you need good eyes. So it's basically a geometric graph, if it means anything to you, but it's roughly property of large SP networks. It's a good approximation. And it has tons of redistributed prefixes that generate tons of LSPs. I was running the stuff over our containerized things, something like 48, high-speed cores, but I was limiting the CPU cores. It could take to 1 or 2 cores, because it's kind of the reality, right? It's not practically relevant to run something. Assume you have 48 cores at disposal for ISIS. It just doesn't reflect reality in any form or fashion. I was measuring standard flooding, which is about 30 packets per second. And I just crank up flooding to 250 packets per second on adjacency, just to push it, pretty far out, where I think practically we will see that even fast flooding will not go any faster. And I'm not talking 2 nodes connected to each other, but serious deployment with high fan-outs, with limited CPU and so on and so on. So the way the LSP injection happened is basically I had 2 to 18 sources on the network distributed in uniform fashion. And I was forcing these guys to reissue all the LSPs, basically bounce up the sequence number and flood the network. And what I was measuring was, we'll see the graph, is LSDB sync delay, which means from the moment I triggered the sources when did I have all the databases on the same checksum, which for all practical purposes, you know, is approximation good enough. How much CPU did all the nodes burn in the network over the convergence? The transmit load distribution, right? It's kind of important. It would not serve a big purpose if all of a sudden the network would be offloaded by certain nodes where experience extreme spikes, right? Because that then lead to its own problems. Receive load distribution, retransmit, drops. I didn't see any drops, like Q drops, this kind of stuff. How many nodes did the reduction in the network, right? So how many nodes do you have to flip this feature on to really see significant advantage of reduction? Because that has to do with the gradual introduction. You can't, you know, assume that 10,000 nodes get overnight flipped on this feature. That's just not how things work. So this distribution is kind of interesting. Like, how much of the network do you have to roll over to really start to see significant improvements? And then what was the flooding pressure? So, you know, did certain you'll see the graphs. It will make sense when you see what flooding pressure means. Okay, so no link flaps. That's something I'm working on, but that will not be that interesting. Although probably people think when links flap, like, oh yeah, that will be interesting. It's not particularly interesting results, I think, because adjacency just to come up take a long time. So I don't think the flood reduction will show up. What will be interesting, of course, does it converge properly when links flap heavily? But I don't have that stuff here. And yeah, everything has been run on Katara, which is a phenomenal tool, just in case you'd be interested. You know, if you run like heavy container loads. And I just give you the results up front, so you don't have to suffer through, you know, the whole smart scope form, or whatever the English word is, of view graphs. So the somewhat surprising result was that it showed...
One question. So,
yeah.
So from what I get it, you're limiting each instance to one or two cores.
One or two cores, yeah.
And you're turning off, you're delaying SPF during the things you're getting up.
Correct. Yes.
Pure flooding. And, yeah, okay.
Yes,
okay.
Because the SPF are skewing the results extremely heavily, very quickly, right? So if once I trigger SPFs, then the SPF starts to consume so much CPU and introduce so much, you know, jitter in the results that it's kind of hard to figure anything out.
I have one question too.
Yeah,
You
shoot.
said you didn't see any drops, but this is simulated network?
No.
Oh, okay.
Well, what you mean simulated is real code running over containers.
I mean, I'm wondering about your queues, right? Like.
Oh no, that's a real implementation.
So
That you will see queue pressure, retransmit, and so on. No, that's the real stuff how we read in production.
Okay.
Nothing like artificial, you know, or throttle or anything like that. No.
So it wasn't just like Linux bridges or.
Linux what?
Like Linux bridges. It wasn't just a.
Oh no, those were Linux bridges. I mean, how the hell do I bring like 100 nodes?
No, that's why I asked.
Oh no, I mean,
so it's not like a line card queue or anything like that.
No. When I'm talking about drops, I meant purely in our implementation, right?
Okay.
Whereas on the boxes I was running, I was making sure that the underlie didn't do, you know, funky stuff. So I basically had the links at unlimited capacity.
So control plane queues, like.
Yeah. That's what I meant. Sorry. Yeah. You know, down to where it push it to Linux kernel, off it goes. Yeah. So the most surprising, somewhat surprising result, but where the stuff was showing enormous gains was actually on the CPU that it was burning. And it was so consistently, you will see, no matter what you throw it, it's about 60% less CPU, which is really massive, okay? So that exceeded by far what I expected and what we were seeing first testing on physical boxes and so on in smaller scenarios. Then the LSP transmit receive reduction was pretty good, you know, like 25 to sometimes 70%. You will see what it depended on, but that was like within expectation, maybe even slightly lower, because, you know, when we were running them on very slow boxes in smaller setups, we were seeing higher reduction. Yeah. The LSTB synchronization speedups were okay. So 0 to 30%. Again, it depends on a bunch of things. So non-neglectable. It's pretty nice if your network converges 30% faster. but it's punny compared to what we're seeing on the CPUs. Giving it more cores actually didn't make any difference. That was funny. I mean, I didn't go to like 4, 8, 16 cores because it's simply not in reality what happens on heavy spikes, If we load one core, we are already being, looked askew, right? You're just an IGP, get out. BGP has 20 million routes, right? You will see that with faster flooding, so that's where things will get interesting. And when you have more sources distributed and more LSP, then the gains go up, right? They start to creep up. So you pretty much have all the practical results. The rest will be like showing you, the details of the stuff. So do not try at home to run something like that. 32 cores water cooled is like a minimum entry, and like quarter tera physical, half a tera physical, if you can even buy the chips, right? Because stuff not available. Massive Xeons work as well, or Docker swarms, right? So don't expect to run any of the stuff on any punny gear. Right, so how to read the graphs? That is the key. So when we run reduction, we show it in blue, and when we don't run reduction, we show it in orange. So it's easy to read. And those are distributions. So it is something like delay versus how many nodes experience this delay. So it's a very classical way to show statistics, right? It can be something. It can be percentages, delays, and so on. Every graph shows it. And it shows something which is called the weighted average, which don't take it like the absolute number, but it helps as a relative comparison between what you get with reduction without reduction, right? This gives you kind of percentage difference. And what you see here is some, like total synchronization delay across the network, right? So the event is somewhere 0, and the first nodes with reduction after about 5 seconds, you see them, right? So like 1, 2 nodes, and then you see a load of nodes. So yeah, of course, it looks pretty classical. I mean, it's mostly, just normal distribution, Gauss curves. Or it can be something like CPU consumption and so on. So that's how you read it. Goodie. So that's like something to warm up. So that runs on 1,000 LSPs, 37 nodes, and 5 sources, right? They look close to each other, they're not, they're randomly distributed. So no, they're basically half a graph diameter from each other. And about 400 adjacencies, okay? And we tickle this thing first. So here's the CPU consumption. So that is normal flooding, and fast flooding is to the right? So this goes 30 per second, and the other thing goes 250 per second, okay? And what you see is that the CPU reduction is very significant, right? It's about 60%. And this is like, so how do you read it? So this is CPU seconds times 10. So that means to the very left that more than half the nodes or something like that experience with reduction 0.5 CPU. And it's measured on ISIS. So, we have all this probing. So this is basically measuring just ISIS until the packet shoots out the box or come into the box. And you see that without reduction, it's shifted to the right very heavily. What was, however, surprising to a certain extent, that once we flip on fast flooding, the CPU consumption goes significantly down again.
Can you define fast flooding?
250 per second.
Okay.
Okay. I didn't want to introduce you to complicated, like we flood like this. No, it was just, this was 30 per sec, spec, and this was 250, which is pretty much opened the floodgate and stopped 250, because otherwise it just becomes practically irrelevant, right? I mean, in a real network, you never get higher speeds. I know that from Rift experience when we were deploying stuff. You just run out, with this amount of adjacency, you just run out of CPU, of scheduling, of everything pretty much, right? So that was mildly surprising, right? And as you see, it was both the case with reduction and without reduction. And that is actually a very good indication that the fast flooding will not only converge faster, but possibly have other good properties. That's all one core now. Now this is the link state database synchronization delay, right? And again, blue is with reduction, orange is without reduction. And you see that just looking at the weighted average is about 40% faster under normal flooding. And it's about the same, a little bit less with fast flooding. And we see also that the convergence behavior with fast flooding is really significantly better, right? Because the graph to the left starts around 5 seconds and this one around 3 seconds, right? So you see that converges about twice as fast because the total is sum, right? It's basically integral over the graph. So if you see over the blue on the left is 984, to the right is 571. So it's almost twice as fast converging on fast flooding. So that's a really good number. No, given that the CPU consumption also goes so massively down. You know, it wouldn't be much of a result if I say, oh, if I gave it 4 cores and it fast flood, it's twice as fast. Yeah, duh, right? Yeah, of course it burns, you know, CPU like it would be going out of fashion, but it is doing on a very low CPU load. Then this is how many LSPs were transmitted. That's kind of interesting, but not even in terms of like total numbers, right? So in this graph, it's like say 40% LSP transmission. But what is of course interesting is that you see that the peaks on the nodes, how much they had to transmit overall were much, much lower. And what do I mean by that? That the blue graph is shifted very much to the left, which means that the node flooded much less LSPs, right? Whereas the orange graph shifts very much to the right. So it's not even that it floods less. There are nodes without reduction that experience much, much higher flooding pressure in terms of what they had to get overall out the box. Which, you know, is where you get into trouble, right? When the box is overheated and start to drop adjacencies, reboot, whatever, right? Retransmit, nada. Here's reduction distribution. So how many nodes did have to kick in? So what does it mean? 10 means 100% reduction. I didn't flood anything, right? Of course, the orange, everybody floods everything. There's no reduction. But you see that the distribution of the blue nodes tells you that with this peak at 40% reduction in volume is that to the right, there isn't much. It's very heavy to the left, which means that you don't need many nodes actually to achieve most of the flooding reduction on the network. So that was interesting. But again, this will all start to shift when I start to play with variables. I try to go at reasonable speed so you can follow, but you know, otherwise digest the preso at your own speed. So did 2 cores, and we're talking, you know, beefy thing like the newest generation, about 5 gigahertz, right, with unlimited memory pretty much. Did that shift the graphs? And as you see, no.
Hey, Tony, I see you have 31 pages.
Yeah, I'm going. Okay. You want me faster? It will become a film. All right, so let's flip it on. So like bigger graph. So what happened here? 1.5K LSPs, 55 nodes, 7 sources, more adjacencies, 630. All right, so CPU consumption, you see the same thing. So that's what I'm giving to the top right kind of summary. Again, 60%, fairly consistent, 20% less CPU consumption on fast flooding. Sync delay, here you see that it is not that it does so extremely well in terms of convergence, right? It's just 30% faster normal flooding. But when you compare fast flooding to normal flooding, and you see the fast flooding, the reduction is not even converging that much faster, right? The distribution is much narrower, but it's like the first nodes are not much faster. But overall, the speed of convergence is twice as fast. So that's quite impressive, right? Just by speeding up flooding, good, you know, by heavy amount, but without the CPU load. Pretty much the same picture, right? But here, because there's so much more load, so many more adjacent, so many more sources, you see the reduction goes to 20%, right? So it's actually, it doesn't reduce massively. And what you, however, see here is, and that becomes a very interesting thing, so that I stop here for a second, that here we start to push the envelope. So it starts to retransmit. Okay, that's normal flooding. Fast flooding, you cannot push out the envelope. It's just, there's just too much air. But with normal flooding, now here we start to walk the retransmission curve. And those are percentage, like how many nodes retransmitted, how many percent, you know. And you see that the no reduction, there were nodes that were pushing to 10 to 12% retransmission, right? And overall, retransmitted twice as much. And that basically means that the envelope under heavy load of your network is much, much better with reduction. It just gives you much more air before things start to really fall off the cliff. Good, even bigger, okay? But less LSPs and very few sources, just 2 sources, right? Bigger network, quite dense, but fewer LSPs and just 2 sources. So what do we see? You see still 60%. But here, the fast flooding wasn't any faster. It didn't save any CPU, right? Fewer sources, denser network. Sync delay, okay? So reduction here didn't give you any speed up in overall sync delay because just two sources, right? So the speed wasn't like it could get the thing everywhere faster. And the fast flooding, still 30% speed up. Not twice as fast, but still very significant. Even bigger graph. And now we're blowing like 1.6K LSPs, right? So the things really start to hit the wall. CPU consumption, again, 60%, right? The fast flooding difference starts to get less and less the bigger the network and the higher, the heavier the load on the network, right? So the fast flooding doesn't save you that much more CPU again. I try to go fast. Sync delay, you see the reduction at about 30%. That's what you get out of it, right? It's not like it will converge 10 times faster. No, it gives you like 30% on very heavy load. The fast flooding here gave you quite good speed up, okay? Retransmission, and now you see how you really start, it really shows that, you know, reduction here, because there were so few sources, actually didn't retransmit at all. And the no reduction starts to blip up. Even bigger graph. Now 0.7 LSPs, and here we have 18 sources. So what happens if you start to inject from a lot of places, on a lot of nodes? CPU consumption, 50% reduction. That's why I said that was the astonishing thing. No matter what I threw at this thing, different graphs, different customer profiles, half the CPU, okay? But with lots of sources, very large networks, with the fast flooding, it was not that the CPU went much farther down. Sync delay, no, here it was like 40%. You know, if there's a lot of sources, then the reduction speed ups actually quite a lot. If there are few sources, no, because it's pretty much the same distance everywhere to get everywhere, okay? And much less flooding pressure, because not so many people are trying to inject new stuff into the network. You see that's the received LSPs, so that's very consistent, that with no reduction, there is a very significant flooding pressure on the nodes compared to no reduction. The reduction distribution here becomes interesting. No, let's skip it. It's not that important. So what about the PSNPs that we use to heal all this stuff? You remember like this, every second, if you didn't flood, send a PSNP, will it generate much more PSNPs and so on, blah, blah. But you would think on the other hand, well, it reduces so much, right? So yeah, don't need that many X. So like, how does it balance? It turns out that the extra PSNPs that you need to tell people that you're not flooding them, and the saving in X pretty much evens out. You end up with roughly the same amount of PSNP overall on the network, at about the same PSNP load. So there, I am only showing one graph because it was everywhere like that. It basically balances. So summary, massive CPU, 60%, 50%, no matter what you throw at it, which for us is the result, right? We're doing it. The good reduction, 25 to 7% in the volume, but it very heavily depended. How many sources, how dense the network, how much per source, etc. The synchronization speed up is highly dependent, again, on sources, on the topology, can go up to 40%, okay? But it can be also about even. Throwing more cores at the stuff doesn't seem to make a difference within, reasonable, practical bounds. When the slow flooding versus fast flooding, what we're seeing that the slow flooding without reduction gets under retransmission pressure much faster, right? I didn't see queue drops, so I couldn't really push our implementation to the point where we went like, okay, I'm just running out of queues. But you saw retransmissions, they started to bleep up.
Yeah, I'd encourage people to put your questions to the list in the interest of time. I think we could discuss these results for the rest of the session, but I'd encourage you to post your questions. Look at them. The slides are out in the meeting materials.
Yeah,
and I think the next presentation there's going to be a lot of comments, so I think we should save time to go to that one.
Les is in the queue.
Okay. Oh yeah, Les. We'll let Les go.
Yeah. So just one quick question. Sounds like there's echo here, but
no, you're good. Hey, Les.
Okay. On the CPU core thing, the fact that you suppressed the SPF frequency,
yeah,
do you think that influenced things? That if you were running
massively so. Actually, so the way I was running it, I was measuring the network, and if I got the measuring results, and I was seeing more than on the 70, 80 nodes, I was seeing more than like 15, 20 SPFs. I was throwing the result away. The jitter got too bad. It affects it massively, yes. So
sorry, but my question is more like, one can imagine that if you had two cores that you might be able to separate the update process from the decision process in terms of where they ran. And since you're not running the decision process as often, you don't get much benefit from that.
Yeah. Fully agreed. If you obviously if you have a database that can run in parallel and you throw SPF on a different CPU, it will make zilch difference. Based on how we implement and what we do, that's not the case for us.
Okay, thanks.
Okay, so there are some aspects of that, but it will become very deep red hole of implementation details.
I would love to see the prof, like the Linux prof, to see where the reduction was, like what was and what wasn't running.
In which sense you mean? So we have our own internal measurement infrastructural implementations. I didn't look at Linux. Who cares about Linux? Kubernetes anyway. We measure the stuff down to like microseconds on our own internal scheduling.
But, I mean, it could, like something like prof will tell you what functions were running, right? Like where was the reduction? What was running that didn't run when you got the 60% reduction?
When you post your source.
I mean, it's precisely the same code. It's just much less processing, much less of the LSP, put it in a queue, compare this to the thing, put it in a database and so on. There is no particular magic that will like shortcut it something massively.
So I'm not doubting it.
Yeah. I don't know what the question is.
I'm the queue. This is a do as I say, but not as I do. I'll ask too. Do you have any counters that you could put in there on how many times those incremental PSNPs fail and you have to resync?
No, I don't have any measure on that because it's very hard to figure out whether it's actually something that fixes the graph or whether it's something that actually triggers because it's valid because the reduction didn't get there. It's inextricable. So we are actually thinking about it, and I want to put in probe which actually do something else. When the CSNP comes, how many times did the CSNP miss? Because, right, so that's what I want to put in as next. Because I try to measure PSNPs, you can figure out what they're good for. Is it an ACK? Is it a request? Is it valid? But CSNPs could give me an indication how many CSNP misses do I see. But then you have to be careful because you're covering with a tree and the other one is trying to saturate all the paths at the same time, right? So yeah, good. Keep discipline. These boys are just asking questions, without any queue management. I tell you.
Yeah, bring up the next.
All right. Yeah, shoot. So imagine the AI variants I was clicking. Yeah, this one's blue. All right. So this is, don't think about the stuff as a final baked solution like some rubber stamping. This is discussion framework. All right, that we line out. So what's the problem, right? We go into the sizes when the CSNPs do become a consideration, both in terms of computing and I/O, right? Databases get to the point where we have to push a lot of stuff over a lot of adjacencies. And the caching and so on helps, right? But we see where it starts to show on the radar when it's worth to talk about what we do with the CSNP. So when we have a stable network, everything converged, everybody asleep, all the CSNP, CPU and I/O is basically 100% overhead, no purpose whatsoever. But it's incredibly useful if anything goes wrong, right? It's the ultimate band-aid. So like I say, caching helps, but doesn't save on I/O. And when the CSNP shifts, database shifts, then it's very hard to keep the caches. You have to nevertheless redo a lot of stuff, add authentication and so on, and you start to see that it's not neglectable. The whole thing of a couple thousand adjacencies and the game gets very interesting. So let's recycle an old idea, okay, which is called Merkle trees. Some guy, 87. And what this thing is good for is basically to quickly synchronize two partitions of data. And the way it works is that it's basically a tree of hashes subsuming the previous level. And we can call it level, degree, rank, doesn't matter. The bottom, we call it the level 0, rank 0, the A, B, C, D, E, F, and those are really CSNPs. Those CSNP entries as we have them, traditional, right? Which is the ultimate source of truth unless the checksum misses, which, is a risk that you take, but we're dealing with since many years. Once you go to this alpha to gamma, now imagine that we take A and B and we build some kind of a hash over it. And we just show the hash and we say from A to B, the hash is alpha. Next game, the capital alpha, capital beta is the same thing. And at the end, you will play the game consecutively. At the end, you can imagine you just have a single capital omega, which is a hash over the whole database. Okay? And if you could just send those hashes around, the volume is significantly lower, right? Assuming those hashes are kind of cheap to compute. And that's the idea behind Merkle trees. And databases have been doing that forever. A lot of modern technologies that is doing that, under the hood. Dynamo, I think, does it, and so on and so on. All right, so now packets carrying this kind of hash goodies, we call them hierarchical SNPs because they're really still SNPs, okay? And we have a hierarchy of those things. Again, mental model, framework for discussion, filled in with a lot of details, but it's opening for good ideas, and whatever feedback comes. So good. So the hard part, of course, is how to partition this database. Yeah. So especially because we have to shove this thing in packets, right? The packets are finite size, so it's not like we can just send a big omega. That won't help much. So how do we partition to stick enough to save, but the packets not to blow out, etc., etc. So what we realized that we need ranges, right? Like here, A to B, that's a range. So we kind of back to the old CSNP formats, right? We have to range from here to there, and the ranges have to be to have a range, and compared to ranges, you need basically ordering. So we basically all back to system ID. So whatever we figure out is something we can order and show a range. So we back to square root one. We basically have to work with ranges like CSNP packets today, right? The same concept. And given that we have the limited packet size, if the alpha and the beta fits into a single, HSNP, we'll have another packet with a gamma. So it doesn't look that different from normal CSNP, except we carry just a range and a hash in it, okay? And we'll get, now, of course, is how much do we cover with the range? We don't want to cover too much, because then a mismatch means that we know that a huge part of the database isn't synchronized, and we don't want to just take a very little, because at the end we end up with so many hashes, it doesn't make much of a difference. So there is something in the draft how to do this partitioning, right? And build it in a way, it has a lot, it looks kind of similar like fragment sliding. You're familiar with the ISI's fragment sliding hell, right? Just fill it reasonably, but if there's a little bit space left, don't be too greedy, maybe start another fragment, because otherwise you start sliding and so on and so on. So that's a discussion, right? How to go about this partitioning. Now, and then, of course, if you receive something on your side and it tells you A to B, there's an alpha hash, but you don't have an A to B alpha hash, you have an A to C hash for yourself, how do you compare those things, right? So one possibility is to use a hash that is very easy to adjust for ranges. The other possibility is to negotiate the ranges, but now you have 500 neighbors. You want to synchronize 500 neighbors on the same ranges, while the database is, of course, flooding and changing for everyone. And then you need, of course, an X, so he knows that we have this range. So it looks like a little bit of a futile complexity exercise. So what we did in the draft, we went in the direction of like how to build the hashes that you can quickly adjust and maintain very, very cheaply. That's, again, just a suggestion. It has pluses, minuses. Okay. So we start with the bag of tricks, right? So we built the ranges only over system ID without a pseudonode. No, a lot less, there was already a lot of discussion on the list going back and forth. So basically, we take all the LSP of a single node, right, including pseudonode, and that's the resolution. And then we bunch those together, all right? Like I said, it looks like a very complex protocol to try to synchronize ranges with neighbors, especially when the databases are converging. I don't even think it's possible. I think at the end, we end up basically building a protocol where we have to agree on ranges before we do anything with database. The moment we do something with database, we have to resynchronize ranges, and the whole thing will be a total pig, to put, a fine point on it. So the bag of tricks is that we use something which is called the self-inverse hash. It looks like a very cool term, but basically it means we use XOR. There's other type, but I won't even talk about it. It's way modulus arithmetic, way too complex. So why is XOR cool? Because it's very easy to update those hashes. Imagine you have a system ID and the fragments are coming in. You just XOR them in on a single hash. You drop the fragment, you just XOR it out. That's why it's self-inverse, right? Let's say you end up with somebody giving you A, B, C, right? And you already have A, B. Well, you just XOR the C, which is the whole system ID, which you already maintained. So it's got awfully fast, right? Very easy also to keep around. But, you have to make sure that your hash function has really good entropy for the XORing stuff. We have to check some, which is a good entropy from the CSNP that we XOR in, but nevertheless. And there is this little problem that the XOR doesn't take sequence into account, right? So no matter in which sequence you put those things together, they will generate the same hash. Maybe that's an advantage, but generally, if you don't take the sequence of an array into a hash, you have lower entropy, right? Because guarantees again misordering. So There are suggestions to use a checksum. That is to be thought through, right? It will probably massively more complicated, massively CPU intensive to maintain because you cannot incrementally add something to a checksum. Well, adding works, subtracting doesn't at all, right? But maybe that's a solution. There is also something, like I said, double hashing, where you basically generate two hashes and then put them on top of each other. It gives you much better distribution of values, a much better entropy overall. And the packing is something like, how should we pack? How loosely should we pack? So the range doesn't blow out, how much fits into a packet. You find all these, mind-bogglingly boring details in the draft as a suggestion from the practical perspective. And right, and the rest is trivial. From both sides come hellos, what's the maximum level you can do? There's one detail that's not trivial. And then if everything is absolutely perfect, everybody sends one packet with a few hashes and life goes on, right? Less perfect world, you realize you have a mismatched one of these hash and you know which rank it's at, which level, and you say, okay, there's a mismatch here. So I have now to decompress everybody those in this hash in one level lower hashes. And the game is played recursively until you fail back to CSNPs, right? So it's basically you back on CSNP exchange. And the tricky part is, of course, that this thing due to its recursive nature and being a virus, because it replicates itself, one miss generates a lot of things all of a sudden, will need some kind of smart pacing. Maybe both sides cannot do it at the same time, maybe there's some limits on these things, and so on and so on. So the draft doesn't say anything about it, but those are, these egregiously, unpleasant details that will have to be hammered out. And right, so those are the things that were thrown in the room, Should we at the beginning when the adjacency comes send CSNPs because we assume the database is out of sync, or should we say, no, they're mostly in sync, so just let's send the hash. Or should we double hash? Should we check some of the stuff? And broadcast adjacencies are completely omitted for the moment. That's it. I don't think I overran
I think we look forward to seeing an update on this. It sounds like there's a lot of stuff that you're talking to with other ISIS developers and everything. A lot of and you can get some more details.
Yeah, that
it
was
would be
just
good to have a problem statement in the beginning that states what you're doing. No, you do, but not the draft itself doesn't, kind of goes right into the...
It's evident.
Yeah, okay.
Obviously.
I didn't use obviously and
No,
clearly.
not in the
I said
presentation.
evidently.
Last is in the queue, yeah.
LS.
Yeah. So, Tony, first of all, thanks for attacking this problem. I think it's something that needs attention, and we've sort of talked about doing something about it, but nobody's actually written anything down. So, really appreciate you starting the ball rolling. We discussed this on the list, so I don't know that we're going to settle it here. I just want to say that the key element of the link state IGPs has always been 100% reliability of the update process. And we're introducing some risk here, and I'm not comfortable with this yet. So we need to do more discussion. We've had some on the list. I think it's going to take time to work through other alternatives, perhaps, or where we want to compromise. But I'm still very uncomfortable with the fact that we're compromising 100% reliability.
I think I refuted this argument comprehensively. Oh, that's a big word. On the list, so I won't repeat the whole thing. All right, checksum can also betray you, and I gave you rough probabilities, lined out what this thing does with the 32 bits hash, so we can continue based on some simulation results, maybe good statistical distribution, because otherwise just feeling and fears. And I acknowledge them, but they, don't bring us any farther. And any alternate proposal, highly welcome. I didn't see anything. And to say I am just, carrying water here, the whole problem is Dave Katz and Tony Lee and some absolutely obscure discussion before I was born. Well, almost. So I sat down and put my nose to the grindstone, wrote some Rust, and scratched my head for a bit, drank some beer, and wrote, like the first detail of what I think we can practically build. Okay.
So I didn't think you were that young, Tony, but
Yeah, I know. Still diapers, man. Yeah.
anyways, this deserves a lot more discussion. But I really
Yeah, that's why I
appreciate
said. I mean,
starting
I
the ball
didn't
rolling.
bother to bring you something rubber stamped. I brought you something that from my rough, sketching around in Rust, basically made a lot of sense. All right, good. So, list. Did I burn enough time?
Yeah. Luis Contreras?
And we burned through all our padding.
Hello everyone, this is Luis from Telefonica. I will present this joint work with my colleague Raúl Arco from Nokia, and we will present some initial ideas based also in another existing work, but basically with a different approach. So the idea is to work on the notion of energy-aware routing. So basically being able to get observability what is happening in the network and reporting with basically ISIS, OSPF, and even BGP. So the motivation for the work is the growing importance on whatever has to see with energy efficiency. For instance, in the deployment of network sound operators, more and more we are increasing the capacity that we are deploying, but the ratio between the peak of the traffic and the value of the traffic is increasing as well. So what this means is that more and more we are generating more vacancy in the network, so it would be good if we can activate some mechanisms for reducing the energy once we have that vacancy and we can somehow consolidate the flows in some few links. So the idea behind all of this would be basically such kind of optimization. So we need then these mechanisms for optimizing paths, for consolidating traffic and so. So what we are proposing here are extensions to some TLBs for reporting that information, the information of the energy being consumed along the time, right? But also incorporating some additional data that could help us to better interpret that reporting of the energy consumption or the power consumption. We also acknowledge previous work on that. There are a number of drafts dealing with the same topic. In fact, after me, Jimin will present something related to this as well, so that there is existing work, but we are basically proposing something a bit different. So what could be the kind of metrics that could be relevant, let's say? We could consider metrics at the level of node and the level of interface or link. And here we could consider metrics like maximum energy, real-time consumption, energy per unit of traffic, and so on and so forth. For the node and for the link, almost the same story, the real-time real-time energy per unit of traffic or the maximum consumption. Certainly, the maximum consumption is something static, so probably doesn't deserve to be advertised continuously, so probably can even be retrieved from inventory, something static information basically, where we maybe can leverage on data sets or models after benchmarking the nodes in the lab and basically creating models. That is for the maximum energy. But for between the minimum and the maximum, we will have the dynamicity there. So that will be the kind of information that probably will be relevant to be reported along the time, right? But as said, we need further information, not only the energy that is being consumed, but information that could help us to interpret that value of the energy. The idea here would be to retrieve information not only from the routers that could enable some dynamic consumption and activation and deactivation of parts, but also legacy devices. And I will go through what we are proposing in a while. So which are the TLBs that we were proposing in the draft? And apologies because I didn't include here the capture, the screenshot of the TLB structure. That would be much more visual. But let me go textually through that. So we are proposing a TLB, a new TLB structure, basically, and we are considering two kind of metrics: absolute metrics and relative metrics. The relative ones will be average along the time, while the absolute metrics will be one shot at the point of measurement. For the absolute metrics, we are considering in the TLB for sure the reporting of the power values with integer and decimal part, but also some other fields that could help us to better interpret that value. We are considering adjustment values, and these adjustment values could be related, for instance, if we, for instance, identify in the lab with benchmarking or whatever, some kind of bias with basically using instrumentation about the reported value, we can use this adjustment value for that. Or even thinking on other aspects like the carbon footprint and so, if we could consider some adjustment depending on the energy mix of the whatever point of presence and so on and so forth. So basically that would be a factor that we can play with in order to modulate the actual measurement that is reported by the router. Also, we consider a default value, and this default value would be essentially for those routers that are legacy ones that basically we cannot even characterize, or we basically need to associate a permanent value. So that would be an indicator of that fact. And also we can consider power modes. Why? Because assuming that in the future the different devices will be able to enter in different power modes or power states, we need probably to associate the reported value with the power state that the node has at that point in time, so that we can interpret correctly that value of energy or power. And going to the relative metrics, basically the information here would be the time interval in which we are averaging the information, and then the information per unit of traffic, sorry. So with this, we consider that we could do some precise reporting of the energy and probably triggering optimization capabilities or consolidation capabilities in some point in time in the network. So we also covering, we provide some ideas in the draft about the integration with the pack computation. Probably this could be out of the scope in this working group, but we added some ideas there. We were considering to consider two kind of scores, one per node and one per link. The node score, at least what we have in mind right now, will be basically aggregating the power consumption of all the device components. And for the link score, summing the power consumption across all the links of the path. And assuming that we can, with this information, we can assign as well some scoring to the path, and maybe the path computation element can take decisions based on that score. These are initial ideas. So probably, as said, probably is not out of the scope of this working group, but okay, we could combine with other metrics and so on so far. Should we go to the question?
I don't know. I thought I was in the queue, but Peter is. Yeah. Am I not in the queue?
You put the.
I clicked it.
Oh. Okay, you're in the virtual queue. You can be next.
Go, Peter.
Oh, you're right there.
Okay, Peter Pshenak, Cisco Systems. So I look at the draft and the other one, which is related to this. You seem to introduce a lot of things for IGPs to flood at the node level, link level. Then you add some, FAT extensions, etc. And the way I look at this, what you try to do, you try to influence the routing to use some of these data. I believe most of the stuff to do that is already there. I don't necessarily believe you need to flood all this. If you want to make a controller aware of this data, you can use some other mechanism. But for the routing component itself, you can use the flagging of the links with the existing affinities and do the exclusion based on that. If you want to somehow turn this into the energy consumption into some aggregated metric, which is advertised per link, you can advertise that metric and use that metric for flex algo. That already exists. And for node exclusion, there's no such thing in the flex algo apart from stopping participating in an algorithm, which again, if the node gets into the state that it consumes so much energy that you want to exclude it, it can just stop participating. So what I'm trying to say is most of the, or all of the mechanisms that you are trying to use are already there. Maybe you can use this and then turn the values that you locally have on a node in one of these mechanisms, and we don't need to flood all this data everywhere.
Okay, thanks for your comment. Okay, probably we need to review all the alternatives that you mentioned for sure, but things like ways of interpreting the values, like the power adjustment and these kind of things, or the power states is not there. So probably we would need to have that information for complementing those existing mechanisms, maybe. If we want to have more visibility rather than just simple consumption.
So that's the question, and we can take this offline. How much visibility do we really need at the routing component level?
Okay.
Thank you.
Thank you.
So my question was, I found myself asking, I know that there's a lot of people looking at energy consumption in different areas, but my question was, how much energy are we talking about here? Because like I know that AI stuff is hugely expensive power-wise. I'm just kind of curious where we are in scale, with routing and the routing, like basically where is that? And I think you don't have to answer that right now, but I think it might be really useful to have that in your document because it gives some justification for doing the work in the first place.
Okay, got it. Will do. Thank you.
I guess I'm next. I was just going to say that it'd be good to get the use cases, because if you're going to have to normalize this anyway, have a normalized metric, and everybody's going to have to use, at least unless you're doing path control and you're tunneling, there's a lot of work done in wireless where they use a normalized network. Now, if the use case says you have to set limits, then you need more metrics so you can set the limits for each, if you want to prune once you go over a certain threshold, or you want to really prefer something, or, then you would need to advertise more. But if you want one metric, you want to do a normalized, like I know we did this with the Monet. There was a real lot of work done to get a normalized metric out of a lot of different parameters that were coming from the wireless link.
Okay. We will explore that as well. Thank you. So going, okay, one more. Yeah.
Wei Chanchong from China Mobile. I have one question about how to measure the energy consumption for the router, because the energy consumption may be related to optical module, related to the LAN card, related to the whole routers. But all those are related to the rerouter or something, something like that.
I don't think we want to cover that problem in LSR. That's a different problem how you measure it, and I think it's a boiling the ocean question.
Okay, yeah, and maybe you.
I agree you need a consistent way to measure it, but I don't think we want to cover it here.
Okay, yeah.
Especially not today.
Yeah, okay, that's a question, because you need to use the real-time energy measurements to adjust something. Yeah.
Okay.
Right. Yeah.
Boris?
Yes, thank you, Boris Hasanov, MWS. Just also similar comment, what power consumption will depend on traffic which is handled by this router. So this power consumption metric may be very well correlated with, let's say, load of this particular router, and you can find out like the direct correlation between those two.
Yeah, for sure, we need better characterization in general and understanding well the dynamics, what is needed power, what is depending on the traffic, and so, yeah, clear.
Okay, thank you.
Thank you.
Tony, the queue's cut, but we'll let you talk. Go ahead.
Just wanted to address Chris's comments. Right now, the rough survey that we've done says that every NPU that's out there consumes about 250 watts. So turning one off does matter. Another data point, BT reports that they consume about 1% of the power budget in Britain. We have to do our part. Even if the AI guys are blowing us by, we still should be doing our part to save some power.
Okay. Well, the final slide was missing, but okay, there are some open questions that we will address in the future meetings. Thank you.
Okay, hello, this is Jimmy. Okay, hello everyone. This is Jimmy from China Mobile. I'm going to talk about flex algorithm for energy efficiency. So in the last time, we mentioned that we can transmit network energy consumption metrics by expanding TLV, IGP TLV, and use flex algorithm technology to establish a low energy plan to achieve energy aware routing. Today, I'll elaborate from these three dimensions: indicator definition, implementation path, and the landing well. So, first, I think so is the page 3? Okay.
You have control of the slides at the bottom of your screen.
Oh. So the first is the definition and the priority of energy consumption indicators. The key to achieve energy aware routing is to clarify how to measure energy consumption. Building on the current work of the Green Working Group, we divide the parameter into two categories: static and dynamic. Static static metrics are inherent attributes of the device determined by design and manufacturing and have nothing to do with the load. Dynamic metrics reflect the energy consumption of the device in different working states, affected by various factors such as the equipment root environment and the power supply, and the evaluation is more complex. So why make such a distinction? The core is to balance energy consumption accuracy and network stability. We do not want to we do not want energy consumption metrics to result in excessively frequent updates of the IGP. So while static metrics are relatively fixed, which can avoid this problem. Therefore, we suggest advancing in stages in the near future. First, establish a low energy plan based on static metrics and gradually expand after the dynamic metric evaluation method are mature. This idea also answers the question raised in the last meeting about the impact metrics updates on the network. So the next is the implementation path and core value of the scheme. We propose two implementation methods. One is centralized deployment, which collects metrics through IGP and BGP and calculates routes by the controller combined with SR technology. And the other is distributed implementation, which directly establish a low energy plan using IGP's flex algorithm technology. Here, I would like to focus on the tidal energy saving logic of the second method, combining the tidal effort of network traffic. When the traffic is large and the load is heavy during the day, forward according to the regular path to ensure the business. When the traffic is small and not at night, we can steer the traffic into the low energy plan and shut down the other devices. So we can achieve the energy saving effect. And this method can not only take into account business stability, but also significantly reduce energy consumption, which is one of the core advantage of the scheme. Finally, regarding technology details to realize the low energy plan, we have expanded the relevant fields of IGP protocols such as ISIS and OSPF. And the specific definitions are detailed in the draft. So if someone is interested or someone who have any question or suggestions, please contact us through the mail list. And still the TLV expansion. So in summary, by establishing a low energy plan based on static energy consumption metrics using flex algo technology and leveraging the tidal effort of network traffic along with the dynamic shutdown of network devices, network tidal energy conservation can be achieved. So if someone who are interested, please check out our draft, and I think that's all.
Okay, I'd advise, this is pretty early in this stage of work, but I'd advise everybody to read it. It's an awful lot of information, and I think that we're going to have to, and some of it appears to be static. So we're going to have to, I think, prune down these number of metrics in a real network. But anyway, it'd be good if everybody would read this and comment on the list. Is there anybody in the queue? No.
Yeah.
Okay. Great. G.
Okay, good afternoon, everyone. This is Jiedong from Huawei. I'm going to give a presentation about this simple draft advertising SRv6s for layer 2 bundle member links in IGP. Okay, here's the background. We know that the link L2 bundle can help to reduce the number of adjacencies when there are multiple parallel links between two nodes. And sometimes the external entity may want to control the flows to steer it into a specific individual member link of the layer 2 bundle. And currently we already have 2 RFC. They specify the IGP extensions to advertise the link attributes for each of the L2 bundle members, and including the SR MPLS adjacent seed for the bundle member. Here, this document proposed extensions and also descriptions about advertise the SRv6s for the L2 bundle member links. The extension will be specified for ISS, for OSPF v3. We just described the applicability of the SRv6s related to sub-TLVs to the L2 bundle member links in OSPF v3. Okay, here first we try to specify which one is a suitable behavior for in SRv6 for the L2 bundle member links. For SRMPRS, the adjacency is used for the bundle member links. For SRv6, we know the end.x behavior was defined to indicate the endpoint cross-connect to an array of the layer 3 adjacencies. Here, and if we use SRv6 associated with each L2 bundle member link of the layer 3 adjacency, it can still be considered as an instance of this end.x seed, as it identifies a subset of the layer 3 adjacency. So we think it is suitable to use end.x seed for this case. And for each bundle member link, a separate seed, end.x seed, should be allocated. Here is the encoding we proposed for ISIS. Basically, 2 new sub-TLVs are defined for the L2 bundle member attributes TLV to advertise the SRv6 and.xcs for the bundle member links in a compact encoding. This one is a sub-TLV for the SRv6 and.xc. Here you can see that for in each sub-TLV, you can carry multiple and.xc for the set of the bundle member links as long as they have the same attributes. And the flags are defined as same as the flags in the SRv6 and.xc sub-TLV, and the behavior is set to the value of the and.x behavior. Here is a sub-TLV for the SRv6 LAN and.xc. It's a similar encoding as the SRv6 LAN and.xc sub-TLV, and here we also specify the field, flux fields, and behavior fields. For OSPF v3, we noticed that the IANA has already set the L2 BM flag for the following SRv6C TLVs, sub-TLVs, but there was no explicit documentation of their applicability to L2 bundle in the existing RFC. So this document adds a description about the applicability of the sub-TLVs under the L2 bundle member attribute sub-TLV for the advertisement of SRv6Cs of the bundle member links in OSPF v3. Oh, okay, we would welcome comments and suggestions, and we already received some comments on the mailing list. That's very helpful, and we would like to continue the discussion, and if there's any consensus, we can move this straightforward document towards adoption. Yeah. Thank you.
Go ahead, Les.
Yeah, so gee, I think we discussed this pretty well on the list, but just to summarize, there's nothing inherently wrong with the idea you have. Unfortunately, it's come too late because we've already specified being able to advertise the index SIDs in L2 bundle members in 9352, the ISIS SRv6 RFC. And so accepting this means that we would end up having two different ways to advertise the same information with all of the potential for interoperability issues. So again, it's a nice idea. I just think it's too late in the game.
Yeah, thanks for your comments. Actually, I'm not sure whether it's too late or not, because to be honest, I didn't notice that the RFCs mentioned the L2 bundle usage in the for the SRv6C sub-TLVs.
You know, there's a very explicit, there's a very explicit reference in the IANA section that says that the index SID is advertisable in TLV 25, which is the L2 bundle member TLV.
Yeah, but the text, there's no text about the description of this SID usage for the L2 bundle member links.
There does not need to be.
Yeah, what I mean is maybe because the RFCs are just published and the other people may also, like me, they didn't notice this or they didn't have chance to realize it yet. So maybe my suggestion is maybe we can have a survey to know whether this has been implemented by any vendors or open source implementations. If the answer is no, we can still have chance to make this change. But if there's a good number of implementation, maybe, as you mentioned, maybe something nice but late.
Yeah, I just say the RFCs, the content has been stable for over 4 years, so it's a long time. Anyways, thanks.
I got a quick one too. I have not looked at the IANA registry for OSPF v3, but I believe it is there as well.
Yeah, OSPF is also the IANA is there.
In the IANA,
yeah, in the IANA
I believe it's there.
Just accept the IANA. There's no, because the RFC there's no, if they search bundle or L2, there's no mentioning of that such word. So people may overlook it. If there's no immediate requirement for the implementation, they may not realize this RCF covered this feature.
Yeah, but that's why we added it to IANA, whether a given specification was applicable to the bundle member. I mean, it's like there are some that are and some that aren't, and IANA is the definitive. I mean, that column that we added it explicitly for this purpose, so people can
Right.
look in one place.
Yeah, I agree. And it has this information, just not sure whether people has already implemented it or not.
Well, it's been specified though. Anyway.
Yeah.
Peter?
Yeah, Peter Pshenak, Cisco. Well, whether it was implemented or not doesn't really change anything. It has been specified, people could have implemented or may be able to implement later. We don't want to go back and de-specify something and replace it with something else. This is not what we do. I appreciate your effort as MS-less. Yes, we come up with a more compact encoding, but on the other side, what is the gain given the SRv6 seed size? It's not as much as we did for the MPLS, where the seed is much smaller. So are we going to complicate things to save few bytes in encoding? I would rather not.
No. But if you don't save, there's more chance to, if you meet the large TLV or multi-part TLV issue for this attribute or sub-TLV, right? Because you not only have the seeds, but you also have the sub-TLVs and other fields. They need to be repeated, right? Okay.
Thanks. Yeah, well, you can discuss this more, but. Who's presenting? Leon, in the interest of time, you're not going to go through the whole problem again, right?
Hi,
Just go ahead.
I'm online. Oh, okay. Thank you. Hello, everyone. This is Lian from China Mobile. And I'm going to talk about the draft of OSPL agency supply chain again. And this is the fifth presentation about this draft, and it has been a long time since last discussion. So this slide briefly outlines the problem background for everyone to recall. And the main purpose of the proposal is to avoid the OSPF temporary black hole, or we can call it a traffic drop during a router's unplanned restart. And the root cause is that the neighbor or the remote router utilize the remaining LSAs before the restart for route calculation. Because their sequence number are higher and they are perceived as newer than the LSAs with initial sequence number generated after restart. So regarding this issue, there is also another document which has also been discussed in previous presentations and mailing list. It's related with the OSPL database exchange procedure improving. Before we go through the two solutions, I want to elaborate the main purpose of this presentation. And following the previous discussions, we have been continuously exploring solutions to reach a consensus and also have made various attempts. Since we have also received the suggestions to merge these two drafts before, so this time we also propose another potential merged solution here for everyone to discuss freely. And after that, we hope to receive the guidance from the working group on what's the next step. Should we move forward with these two drafts separately or look into a merged version? So this is the purpose. And this page is a brief review of these two solutions. The general idea, we call it the solution A and the solution B for short. And the general idea of solution A is for the restarting router notifies its neighbor to surprise the agency until the notification cleared. And for solution B, the general idea is that the neighbor router marks its LSA as a still and hold the neighbor state machine until the still LSA list is empty. So the key difference of these two drafts lies on the on which side to control the activity. We have also elaborated in the previous presentation their disadvantage and their advantages. And this slide shows the general idea. It's just a simple one of the merged solution. So the general idea is that we hope the solution A and the solution B can be supported on the routers independently. For example, some routers can support solution A and some other routers maybe support solution B. So which solution to adopt especially depends on the support situation of the equipment. Maybe, for example, maybe some equipment does not have the ability for the signal the SA indicator sending. So maybe the solution B can be adopted. So this is the main idea. And I will elaborate from the two sides of the router. First is the router A. If the router A has the capability for the SA indicator, and it can send the indicator when we start or start, because this solution also applied to the start scenario. And also at the same time, it set the SA timer. And when the SA timer expires, it can clear the indicator and also notify the neighbor router. Or else, it will do nothing for the router restarting. And for the router B, there is two branch. And if it recognizes the SA indicator, it can adopt the solution A. And if it doesn't recognize or else the router A doesn't send the SA indicator, I think it can adopt the solution B. This is the main idea. And that's all. I think all the information I have finished. And so next, I would like to listen to the opinions of the working group. Thank you all.
Okay. Thanks, Leanne. This AC Arcus, I'll take it to look at our solution, see if make sure the one that doesn't require more signaling to make sure, see if I can get the complexity to where I think, but I don't think we'd want to merge. That's my opinion. I don't think we'd want to implement both. If you're, and we'll see if I can cover all the case, make sure we cover all the cases. I haven't looked at this for some time, but as I become infamous for, I'll look at this on the plane on the way back.
Okay, thank you. But maybe first, I think we must resolve or address the problem or questions which has mentioned in the mailing list. If for the solution B, and honestly, from my aspect, I think that not all the scenarios can be addressed using the solution B. So I think that maybe you can refer to the mail list and response the questions so we can move forward this problem. Since it has been a long time since I remember that it's about almost 2 years.
I think we got to give Wei Cheng his thing, and then we got to go to the next one so we get this SABNet requirements in.
I'm also the cause of this draft. So, the both drafts have been discussed several times. I would like we can make a decision because both of them, I think, they can solve the issue. And I hope we can make a decision. Maybe offline we can have some more discussion on that.
Yeah, I'll take a look at it. I promise this time.
Okay, thank you.
Thanks.
Okay, thank you, Izzy.
Hello everyone, Lan Cheng from Zhongguancun Lab. I'm going to introduce this document, but this document is actually in the SABNet working group. So I will first briefly introduce why I requested the presentation for this document.
I'll summarize what he was just saying too. We thought that the SABNet group would like input from us, or at least have our eyeballs on this, because it's probably, the work they're doing there is probably going to come back here in the form of extensions to the protocols. Whether we, if you don't like that, then the point is pay attention to what's going on here and then go to the SABNet working group and put your input there before the extensions get written up in documents and start coming back to us.
Or at least the best current practices how to do it in inter-domain, even if it doesn't require extensions.
Okay, thanks. Yes, and this informational document includes a gap analysis of the current operational intra-domain solve mechanisms and the informational requirements for technical improvements. And this is the document history. And in this year, in April, this document was returned to the SABNet working group, and because of some main concerns. First of all, the standard protocol changes must be based on standard track requirements, but the current requirements are informational. And also, the concern about some terms in this document are not clearly defined. And our responsible AD gave us the suggestions to share the latest version with the impacted working group, such as LSR, to get broader input. And we might consider splitting the document into two parts. One is an informational document, and another one is a standard track requirement if IGP extensions would be required. And in May and June, we shared this document with LSR on the mailing list. And this time I request this presentation to help LSR participants become familiar with this document and its background. And thanks. And before I introduce this document, I'd like to make the following clarifications. First, no IGP extensions are currently foreseen. That said, the future solution may not extend IGP. And this document doesn't describe any solution design or protocol requirements. This document only focuses on the problem and gap analysis. So any protocol changes, if we need any protocol changes, we would require another standards requirements document. And there are the three important terms. And the first one is the subnetwork. It is an IGP domain, routing domain, but is considered part of the AS. Is connected to one or more routers for outbounded connectivity, but is only originates traffic and doesn't transit traffic. AC just give us a suggestion on this term. Thank AC. And if anybody think this term should be modified, please let us know. And the improper block and improper permit. The improper block means the validation results that the packets with legitimate source IP address are blocked improperly due to the inaccurate subrules, while improper permit means the validation results that the packets with spoofed source IP address are permitted improperly due to the inaccurate subrules. And we distinguish the from the intra-domicile and inter-domicile based on their capability. The intra-domicile is for an AS determines subrules by the AS itself with its own information, such as the local configuration or intra-domain routing information. While inter-domicile for an AS requires information, such as BGP, provided by other ASs to determine subrules. So there are two use cases for intra-domicile. First is for traffic originating from the subnetwork or host within the AS. They are the entities which only originate traffic but not transit traffic. So intra-domicile would prevent the subnetwork from using a source address out of the subnetwork or prevent a host from using a source address out of the network segment. And for the second use case is for the traffic sent from the rest of the internet. It can prevent spoofed data packets coming from the rest of the internet that use a source IP address of the local AS. This is different from inter-domicile because inter-domicile can identify the spoofing traffic from other ASs if it uses a spoofed source IP address of another AS. And we summarize three current operational intra-domicile used in practice. They are ACL-based ingress filtering, strict UIPF, and loose UIPF. And we provide some gap scenarios to introduce the problems and the reasons behind their problems. In summary, the ACL-based style has the problem of high operational overhead. It's because it entirely rely on manual maintenance. So when network changes, when the prefix or topology in an AS changes, the operator must have to update the ACL rules immediately. Otherwise, it will improper block legitimate traffic. And for strict UIPF, it has improper block problems under asymmetric routing and hidden prefix scenario. The asymmetric routing means the traffic sent from the source to the destination use one path, but the returned traffic from the destination to the source use another path. that is asymmetrical routing. And the hidden prefix means a host which is only reachable while one address, but it may use another address as the source IP address when it sends out traffic for some reasons, such as the direct server return, IP multicast, and such examples. And in these cases, strict UIPF will have improper block problems. It's because it solely uses the router's local FIB information to determine subrules, which may not match the incoming interfaces of legitimate data packets from the real source. And for loose UIPF, the main problem is the improper permit because it allows any spoofed data packets using a source address covered by the FIB. And finally, we provide 5 general requirements. The first 2 requirements are exactly targeted at the problems, and the last 3 requirements are common requirements for any possible solutions, regardless of whether it will need IGP extension or not. That said, we are not assuming that future solutions must extend IGP. Yes, this is just a brief introduction to this document, and if you have any interest in this document, you can have a review of that document, and your comments are welcome. Thanks.
Thanks, Lan Chen. I advise everybody to take a look at this and provide your comments. Maybe you're going to have another revision based on discussions.
Yes, and
maybe review the next one.
Yes, and maybe we would like to learn more suggestions. And finally, after that,
I was just going to say we're going to have a new rule in LSR. Anybody who takes more than half the time and doesn't stick around for the other presentations has to go later in the schedule next IETF.
Tony left.
Yeah. Thank you.
Thank you. Okay, I think that we made it. Anybody with any last comments? I think otherwise we're done. All right. Thanks, everybody.
Sí.